Okay, I'm going to solve the midterm. Question 1. An array of integers named CA contains the estimated population of California every 10 years. So, the number of elements is only 11. We've got one for 1900, one for 2000, and so for instance, this would be for 1920. It gives us an example that say that item 0 is the population in 1900. So what about the population change from 1940 to 1960? Well, you compute a change just by subtracting the later value from the previous value. So that would be ca.item 6, that's the 1960 value, minus ca.item 4. This C is not supposed to be capitalized. But the software capitalized it for me and I'm too lazy to change it. Okay, moving on. Whether the population ever grew by less than 500,000 in a decade, represented by this array. Well, we're going to have to figure out changes by decade. That means subtracting the third from the fourth and the fifth from the sixth in order to figure out what are the changes every year. On the study guide, there's a built-in function to do that. It's called np.diff. So if you take np.diff and pass in the array, what you get is a length 10 array that has the differences between adjacent elements. Now what we'll do is check and see if any of those are less than 500,000. So I'm just translating what's in the question into a Python expression. Now, this is going to give me an array of 10 true or false values. So it'd be something like false, 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 if there was never a decade that grew by less than 500,000, or if there was one, then I'd have a true somewhere in the middle of an array. Now, if you look at a question that asks for whether something is true or false, we need to take that array of trues and falses and turn it into a single value that's just true or false. And one way to do that is to use np.any, which is a built-in function that tells you whether any of the true-false values in an array is true. So I'd say in general, we can take a step back and see what's a good approach to solving these problems. Well, one thing you want to do is understand the kind of value you're supposed to generate. So the population is a number. And you get a number by taking a particular item from an array full of numbers. And so you can also get, so this is a number and that's a number. And if you subtract one number from another, that's another number. Now what about this whether the population ever grew? Well, it tells you at the end it should be true or false. So we can see when we generate a true or false value, this expression gives us an array of numbers. This expression here gives us an array of true-false values, something like this. It happens to be that they're all false, but you can't really tell that because some of the values are missing. But it is true, it happened to be false in the actual data set of the population of California. And then, now that we have an array of true or false values, we have the wrong kind of thing. So just leaving it at that won't give us the right answer. To get the right answer, we need to take all those values in the array and get just one value out, and that's why we say np.any, to combine all the trues and falses into one single true or false value. Okay, now the next question says the annual growth rate from 1920 to 1930. We need to know the definition of growth rate in order to compute that. So first of all, we get the decade-long growth rate by dividing the population in 1930 by the population in 1920. Once I've done that, I need to convert it into an annual growth rate. And an annual growth rate is computed from a decade-long growth rate by raising this to the 1/10 power, because we want a growth rate that, if it was compounded 10 times, would give us the decade-long growth rate. And then you have to subtract 1. And why is that? Well, a ratio is different than a growth rate, and it assumes that the 1 is already there. So the population in 1920 is already there, and we're only interested in what was added as we went from 1920 to 1930. Here we'll quickly check to make sure we got the right kind of value. That's a number, therefore that's a number. When I raise a number to a power, that's a number too. So we just have a regular number, which is a growth rate. That's just fine. Okay, the population in 1924, assuming a fixed exponential annual growth rate from 1920 to 1930. You may use the name G for the annual growth rate. So it's as if we had said G equals. And now we can use G again. When you apply a growth rate, you have to take the original value, that in this case would be the population in 1920, multiply it by the total growth after 4 years. Going from 1920 to 1924 means I take G and raise it to the 4th power. So that's 4 different years of an annual growth rate. Now that's not quite right either, because the growth rate of 20% doesn't include the original value. So we have to include, if the growth rate's 20%, then we want 120%, which is what we're multiplying in 4 times in order to reach the actual total value of the population in 1924 under this exponential growth model. Okay, last one, the number of items in California that are at least twice as large as the population in 1960. Here, we're going to end up comparing an array of values to a single constant. That single constant is twice the population in 1960. And we want to see how many times it's the case that's less than or equal to some value that's in the California array. So this is also just something you need to know about arrays. That if you take a whole array here, which is 11 different numbers, and you compare it to a single number, what you get back is an array. So this whole thing is an array of 11 different true or false values that tells you for every element in CA, is it larger than this constant value you've computed here? Now the last part of the question is how do you get the number of items instead of just a bunch of true-false? And there you need to know the name of the NumPy function that computes that for you. And it's on your study guide. It's called np.countNonZero. So that will tell you how many true values there are. All right, I give up. So, forget all this. The actual solution is 2 times ca.items like that, except for you have to call np.countNonZero on the array of trues and falses. There we go. Okay, so what you get here, this is an array, therefore this is an array, but np.countNonZero is one of the kinds of things that takes an array and gives you back a number, the number of items that are, for which this expression is true, which means that are twice as large as the population in 1960, which is here. All right, that's problem 1. Let's do problem 2. You have 1,000 different shirts in your huge closet. Each morning, you pick one uniformly at random and then put it back. This is sampling uniformly at random with replacement, because you put it back at night. Write a Python expression to compute the chance during a 30-day month that there is at least one shirt that you wear 2 or more times. This is equivalent to the birthday problem, except for instead of having 365 days in the year, and each person just has one of those birthdays, we have 1,000 different shirts. How many people are in the classroom? Well, there's 30 days in the month, so that's how many elements we're selecting at random. So the goal here was just to understand how you make the computation in the birthday problem, just like in class. we talked about the way to figure out what's the chance that there's at least one shirt that you wear 2 or more times, as 1 minus the chance that you picked a different shirt on each day, or that each person had a different birthday. So we're going to have a 1 minus, and then the general form will be, well, if you only picked 1 shirt, then you definitely have a new one. But if you picked a second shirt, well, then you'd have this 999 out of 1,000 chance of picking a different shirt than the first shirt. Assuming you had just picked 2 different shirts, the third shirt you pick has to be one of the 998 that you haven't picked yet, etc. And the way you write this as a Python expression is 1 minus, but then you have to write out a range that contains all of these numbers. So one way to do that is to say np.arange 30 divided by 1,000. So what's that? Well, that's, we've got 0 out of 1,000 is the first element, 1 out of 1,000 is the second element, 2 out of 1,000 is the third element, etc., all the way up to 29 out of 1,000. So this expression gives us that array. If I take 1 minus that, then this expression here gives me 1,000 out of 1,000, 999 out of 1,000, 998 out of 1,000, etc., all the way down to 971 out of 1,000. Okay? And then we need to combine all these numbers together. Okay, so if you've computed this array so far, which is great, you then need to multiply all of those numbers together, which is np.prod. So that gives me the product of everything in here. Once I've multiplied all those together, then I see the only thing I'm missing is this 1 minus at the front. Okay, so that's a solution to the problem. And the reason we studied the birthday problem, if you remember, is that these chances also appear when you're sampling with replacement from a table. So if you pick out the rows from a table, for instance, because you're generating a random sample, then this is a chance that you'll pick all different rows. Okay, next problem. The table named twins has a row for each pair of twins that contains the height of each twin in inches. Okay, so this is a description of a table, and we're going to have to do some computation based on that table. And the following code computes the average absolute difference in heights among the twins. Let's see how it works. Well, we have a function that takes in 2 different heights, those are numbers, subtracts one from the other, and then takes the absolute value. It doesn't matter what order these come in because we're taking the absolute value anyway. Diffs is a table with only one column called absolute differences. And the way that this table is filled up, okay, so this creates an empty table. And then what's going to happen next is we'll append rows to that table. So we're going to go through for every I, starting at 0, going all the way up to twins.numRows. So that's the number of rows in the twins table. We're going to find the twins column 0's ith element. So that's like the ith twins, first twins height. And this is the second twin's height for the ith twin. So these are, in fact, comparing 2 different twins in the same twin couple. And we call our diff function, that's this function that we defined up here, in order to compute the difference between the heights. And append that to the table, and then we take the mean, which is the same as the average, of all of the diffs that we've computed. Okay, so then it says complete the expression below to compute the same result without calling diff or using a for statement. In order to do that, we're going to have to do some array manipulation. So the array manipulation that we're going to do takes advantage of the fact that if you subtract one array from another, you get the differences of all the corresponding elements. So you don't have to get item I from one column and item I from the second column and then take the difference between them. Instead, you can just subtract one column from the other. So what that looks like is twins.column 0 minus twins.column 1. Right? So those are the differences between the heights of the twins. Now how do you get the absolute differences? Well, you just call absolute value on the resulting vector. And it doesn't matter whether you call abs or np.abs, you get the same answer either way. Okay, so now I have the absolute difference between each pair of twins. I'm interested in the mean of that, so I just say np.mean or np.average. Let's go through that same exercise that we did before of figuring out what kind of value we're computing in each case. Okay, so here we have an array of numbers. Here we have an array of numbers. When I subtract one array from another array, I get an array of the same length. I've just subtracted the corresponding elements from the second column from this first column. When you call abs on an array, you get back an array. That's an absolute value of each element of the array. And mean is one of those functions that takes a whole array and gives you back a number. So it's just at the very end that we manage to compute the average absolute difference in heights, instead of just all the different absolute differences. So if you, so it is true that the code that we wrote, oh, sorry, I got this wrong because mean is already here. So you're not supposed to duplicate. I was going to say the English maps onto the code. So we have average is the mean. We have this part that says absolute is our call to np.abs. And then the last part is this difference in heights, which is the difference in the two columns. What a mess. Well, let's move on. Each row of the trip table from lecture describes a single bicycle rental in the San Francisco area. Durations are integers, times in seconds. We're going to manipulate this table, write a Python expression to compute the value for each thing. These questions I'm actually going to just solve in a notebook so you can see the intermediate steps and what they generate. So the number of rentals that started at the SF Caltrain station. Well, here's the trip table itself. SF Caltrain is one of the values in the end column. So if I write trip.where end is SF Caltrain, hey, sorry, I did it wrong. The question asked starting at the SF Caltrain station. So that's a different column. Okay, that's many fewer, 25,000 rows. Now, this expression gives you back a table. If you actually want to get the number of trips, there's one row per trip. So we ask for how many rows are in this resulting table. And that's the solution we're looking for. Next was the average duration for rentals that started and ended at different stations. This question requires us to use the alternative form of where we say where and then we give an array of true or false values. Those true or false values are the result of calling column start and looking at where that's different from column end. So each of these is a big long array. And now we have true whenever the corresponding values and start and end are different. Now the length of this true-false array is the same as the length of the table. But if we only take the true values, which happens when you write trip.where, you end up with a shorter table, 333,000 instead of 338. So we've eliminated all the trips that start and end at the same place. Now the question says the average duration for the rentals that started and ended at different stations. So now we have to get the duration column, which is an array of numbers. The average duration we compute by calling average on that array. The name of the station where the most rentals ended, assuming no ties. In order to figure out how many rows correspond to each end station, we're going to need to group. If I say trip.group by the end station, what I get is a table that tells me for each end station how many different rows had that value, which is the same as saying how many different trips ended at that station. So grouping does take a while because there's 300,000 some rows. At the end of the day, we only get up the 70 stations and the count of how many trips ended at each station. Now looking back at the question, it wants the name of the station where the most rentals ended. In order to find the most rentals ended, we're going to have to sort by the count column of this table. And we want to sort it such that the largest count, the number that's the most trips ended, is first. So we write descending equals true. Now once we've done this, we're going to end up with a table with the same format. An end column and a count column. The end column is what contains the name of the end station. And since we've sorted, the one with the highest count will be at the top. That's item 0. So it's going to go ahead and group everything, sort the grouped rows, find the column that contains the name, and take the name of the station where the most trips ended. Okay, finally it says the number of stations for which the average duration ending at that station was at least 300 seconds. This is a challenging question. It asks for the average duration for a station. So that's different from the average duration over all trips because we need this statistic for each different station separately. That's another instance of group. So we're looking for ending stations, that's what we group by. But instead of counting trips, we want to average the duration of those trips. So you can start with the trip, you still group by end, but then you say, instead of just counting up, I'd like to take the average of the other columns. Running this will give me back a 3-column table, because I started with a 3-column table. It will have all the unique values for the end station, and then in the others it will have averages. Now there's no sense in which you can average a bunch of starred stations. That doesn't really make any sense, so that's why these are blank. But you certainly can average the durations because those are just numbers. And so here we see the average duration for each station. Now some of these averages are 400 and some of them are much larger, like 800. The question asked, when are the average durations at least 300 seconds? So the next step is to get column 2, that's the duration average column, and figure out when that's at least 300 seconds. So running this expression, we'll group by end station, average everything, just get the averages themselves, the average durations, and figure out which ones are greater than or equal to 300. And we'll get back an array of true and false values. Seems like there's a lot of trues, but we haven't seen the whole thing. We have one row for every different end station. Those were 70 of those. And we're asking how many of them had this average duration greater than or equal to 300 seconds, which is just 5 minutes. In order to take a bunch of true-false values and get a single number of how many of them are true, we can count non-zero the result, and that will finally give us the answer that we're looking for. The number of end stations for which the average duration was greater than or equal to 300 seconds. Turns out it's all of them. But if this were a larger number, like 500 seconds, then we'd find that that was only true of some of them. Okay, so just to review, we still want to use the strategy we had before of making sure we're getting the right kind of value out. So here we had a table, dot where gives you a table, dot numRows gives you a number, and that's why we got the number we wanted. Here, trip was a table, dot where gave us a table. The argument, dot where, was an array, which we got by comparing two arrays, that's fine. Once we have this table, we ask for a column of that table in order to get an array, and then we took the average of that to get a number. Trip is a table, group gives a table, sort gives a table, column gives an array, item gives a number. Trip is a table, group gives a table, column is an array. Comparing an array to a number gives another array. Calling count non-zero on an array gives a number. Okay, two histograms of bike trip durations below were both generated by trip.hist using different bins. So the interesting thing about this problem is this claim that the same table generated both histograms. So trip is a particular table of all the trips. Trip.hist would be something like trip.histogram of the duration column with bins equal to, and then in this case we have bins that are all 200 wide. So we have 0 to 200, we have 200 to 400, etc. And you can see that because the 200 lines up with this line. So this is the 200 line, that's the 400 line, etc. Now in this histogram, the 200 line actually falls here. So this bin does not go from 0 to 200, but instead goes from 0 to 300. This one goes from 300 to 600. This one goes from 600 to 900, up to 1200, and then the last bin goes all the way from 1200 to 1800. Now, both of these are describing the same group of duration numbers. They're just binning them in different ways, and we'll use that fact in order to answer the questions. Okay, so the first question says, between 200 and 400 seconds, what proportion of trips fall into that range? We can read that directly off of the first histogram if we know how to interpret histograms. And here's the rule. If you have a particular range that corresponds to one of the bins, then the proportion of all duration values is the area of that bin. So this bin is represented by a rectangle, and we want the total area of this rectangle, which is its width times its height. Now its width is 200 because it goes from 200 to 400. So you might write that as 400 minus 200, or it's fine if you just wrote it as 200. Its height is measured here on the vertical axis, but notice that the vertical axis is in percent per second. So this number is not 0.15, but instead it's 0.15%, because that's what it says as the label on this axis. And we always write histograms in this way. Okay, so that means that we're multiplying the width by the height, which is not 0.15, but instead 0.15%. So we have 200 times 0.15 divided by 100. The 200 and the 100 can kind of cancel out, and we get 2 times 0.15 equals 0.3. That's the proportion of 1 of the trips that fall into this range. It's also common to write this as 30%. These two are the same number. Okay, so that's how you interpret a histogram. in order to get the range 300 to 900, we can use the second histogram. So the proportion that fall in the range 300 to 900 is the proportion that fall in the range 3 to 600 plus the proportion that fall in the 6 to 900 range. Every duration is different, so it has to fall into one of these bins. We can add bins together in order to complete a larger range. Okay, so just like before, we need the widths times the heights of these two. So we have a width of 300 times the height. Looks like it's right about 0.14%. And then we add to that the width of the next bin, which is also 300, and multiplied by its height, which was right about at 0.08%. So, you can cancel out all these zeros again. You get 3 times 0.14 is 42%. Another 3 times 0.08 is another 24%. And you end up with 66%. Okay. Now, this is between 400 and 900. You actually can't read that off of this histogram alone. And why is that? Well, the number 400, which is here, isn't at the boundary of a bin. And you don't really know how all the durations are distributed within this bin. They could all be the same, or there could be a bunch at 200 to 300 and many fewer from 400 to 600, which is in fact what happens, because you can see that in this histogram. So instead, we're going to have to combine two bins from different histograms. And this only works because both of these histograms were generated by the same table. So they contain or describe or visualize the same values, just in different ways. So how do we go from 400 to 900? Well, what we can do is get everything from 400 to 600, which is this one, plus everything from 600 to 900, which we've already computed here. Okay, so the one on the left has width 200, and its height is 0.14%. And the one on the left, on the right here, is width 300, and its height looks like 0.08% again. So if you work out the math, this comes out to 0.52 or 52%. Okay, last one. Between 200 and 300. Well, again, you can't read it off of the left or the right histogram, because you can't just assume that half of the 200 to 400 range falls in the 200 to 300 range. So 300 is here in the middle, and that's the problem. But what you can do is take all of them that fall in the 0 to 300 range and subtract out all the ones that fall in the 0 to 200 range. So the range 200, if you take a number line, and you go 200, 300, 100, and 0, we're going to take everything in here minus everything in here, and what we'll be left with is everything in here. Okay, so that means we need the area of this one. That's 0 to 300, which is 300 wide times about 0.07 divided by 100 tall. And then we can subtract out the 200 wide one here, which has a height of 0.05. Which comes out to 0.15 or 15%. There's other ways to solve this problem, like we could have found everything from 200 to 600 by adding up those two bars and then subtract out 300 to 600. And all that would be left is 200 to 300. If you do it that way, you get, just like rounding off the bars, you get 16% instead of 15% maybe, but the same basic idea. So the point is that sometimes you can figure out the proportion of trips that fall into different ranges from a histogram that are different than just the ranges that are shown, because you can add together different ranges in order to get the total. Okay, Frank Underwood conducts a poll to estimate what proportion of voters approve of his America Works program. He found that voters he polled give the program an average grade of 6.5 with a standard deviation of 1.5. So one standard deviation would go from 5 all the way up to 8, and then two standard deviations would go from 3.5 all the way up to 9.5, and three standard deviations would go from 2 all the way up to 10. 10 is the maximum. I mean, the three deviations would bring you up to 11, but you can't get a score of 11. Okay, the first question is, no matter how the distribution of grades looks, what is the maximum proportion that could have given the program a grade lower than 2? So this is the 3 standard deviation case. 2 is 3 standard deviations below the mean. Chebyshev's inequality tells us that at least 8/9 of all grades must fall within 3 standard deviations, or 1/9 can fall without. So that's the answer, actually. It's just that there could be 1/9 of them that are lower than 2. You know, 8/9 fall in the range 2 to 10. Okay, if the distribution is symmetrical and has a bell shape just like a normal distribution, what proportion of those polled gave the program a grade lower than 2? In a bell-shaped distribution, we know more than just Chebyshev's inequality. We know that if you go out 3 standard deviations, and the total amount in the range of 3 standard deviations is 99.7%, which means outside of the range is 0.3%, but that accounts for the ones that are above and the ones that are below. So we have to divide that by 2, and we get something like 0.15%. Or if you actually look at the decimal expansion, which you can find in your study guide, perhaps slightly better answer would be 0.14%. Yeah, same kind of thing. Okay, so this is like a really small number. Now you might have been slightly suspicious of this question because it says it's symmetrical and has a bell shape, but this is something that's bounded between 0 and 10, so there's no way that it really could have a normal distribution, because normal distributions kind of go forever in both directions. But it's not uncommon that you'll see a normal distribution, even if there are bounds, for almost all of the distribution, and just like they get cut off at the tails. So a typical exam score might look like that. Okay, a study followed 369 people with cardiovascular disease randomly selected from hospital patients. A year later, those who owned a dog were 4 times more likely to be alive than those who didn't. This is actually based on a real study, by the way. The study is a randomized controlled experiment. The answer is false. For that to happen, it would have to be the case that an experimenter chose who got to own a dog and who didn't, because the dog ownership is the treatment and being alive is the outcome. The study shows that dog owners live longer than cat owners on average. Well, this is actually false too, because this says nothing about cats. No cats. And that's not a surprise. I generally don't put cats on exams. So this says that people who owned a dog lived longer than people who didn't own a dog, but that's different than cat owners. So you have to make sure you know what your study is talking about. And finally, this study shows that for someone with cardiovascular disease, adopting a dog will probably cause them to live longer. This measures an association among those who own a dog and those who do not, but associations do not imply causation. The answer is false here because adopting a dog will cause is a causal statement, and we have no evidence of causation here because we're not running a randomized controlled experiment. Okay, we're almost done. 8 points left. The ball table contains player data from some of the Golden State Warriors. Only the first 5 rows are shown. You have computed the following summary statistics. What is the value of Steph Curry's points per game in standard units? Steph Curry's points per game is 29. In order to get standard units, you subtract out the average points per game. So this is column 2 of the table, which means that the average points per game is the average of column 2, which is 13. So 29 minus 13 is 16. And then you divide by the standard deviation of that same column. So if we divide this by 8, we find that Steph Curry's points per game is 2 standard deviations above the mean. What is the slope of the regression line when the points per game are plotted on the vertical axis, the minutes per game are plotted on the horizontal axis, and a regression line is fit to the data? That's the slope of the regression line computed by the slope function. Okay, so you just have to know what's the equation of the slope. That is the correlation, 0.75, times the standard deviation, the y values, which is points per game on the vertical axis, divided by the standard deviation of the x values. So we multiply this by 8 over 10. And what's 3/4 times 8 over 10? Well, it's 6/10 is 0.6. So the slope of the regression line in original units is not the same as the correlation. You have to multiply by the ratio of the standard deviations. Okay, so here we're trying to estimate the points per game from the minutes per game. One way to do that is to take Steph Curry's minutes per game, convert it to standard units. So minutes per game is 34. Minus the average minutes per game is 24. Divided by the standard deviation of this minutes per game is 10. Okay, so now we have that in standard units. We multiply that by the correlation, which is 3/4 or 0.75. And then we want to get it back out of standard units. So you get it back out of standard units by multiplying by the standard deviation of points per game and then adding back in the mean. Mean points per game is 13. So just working this out, 34 minus 24 is 10. 10 divided by 10 is 1. So this is 1 times 3/4 times 8. Well, that's 3 times 2 is 6. And 6 plus 13 equals 19 points per game. So according to the regression model, he's only supposed to score 19 points per game. In fact, Steph Curry scores 29 points per game. So he's an outlier in terms of the number of points he scores relative to the number of minutes he plays. So then it finally asks, what would the fitted value of points per game for a player who scored 34 minutes per game change if Steph Curry were removed from the table and the regression line recomputed? Well, Steph Curry being above the line, because he actually scores 29 points instead of 19, is increasing the expected number of points per game for someone in his area of the regression line. If you took him out, and that pressure to have a higher score on average for people who play 34 minutes would decrease, and so the line would drop.